In this lecture, we show how the basic definition of electric power can be used to determine unknown currents and voltages in an electric circuit. We relate electric power to energy and show how the principle of energy conservation can also be used to solve for unknown voltages or currents in a circuit. Recall that the power supplied or absorbed by an element in an electric circuit is related to the current through and the voltage across the element by the following relationship. The power is the product of the current with the voltage. Now we might also write this a little bit different for the special situation of direct current or DC, when the voltages and currents do not change in time. Of course, for both of these equations, we need to be careful to apply the proper sign convention to distinguish between power sources and power sinks. Now, as an example, suppose we know that the current through an element is 5 amps and that the element absorbs 20 watts of power. We know it absorbs because the power has a positive sign. Now, if we use the proper sign convention, then the equation for the power associated with the element would need to know the polarity we're going to assign with our definition of this voltage. So let's begin by assigning the positive side there. So in this case, this voltage tells us how much the voltage increases or decreases as we move from this side to that side of the element. Now in this situation, the power, as the current arrow enters on the positive side, will have a positive current times V1, the voltage. So that tells us that the voltage is going to be equal to the power divided by the current, which in this case is 20 watts divided by 5 amps, which would be 4 volts. Now let's see what would happen if instead of the negative to positive polarity for a voltage, we defined it in this direction. Well, in that case, the power would be this current. It would now enter on the negative sign, so we'd put a negative sign here, I times V1. So V1 would be negative P over I, which would be negative 20 watts over 5 amps, and we'd get negative 4 volts, which would be appropriate because in this case we've defined the polarity in the opposite direction. Well, let's look at another example. Here we have an electrical element that's absorbing 40 watts of power with a voltage of 5 volts across as measured from the top to the bottom of the element. It's worth noting that as in our previous example, this cloud on the left that's attached to the nodes of labeled A and B, that represents some other possible circuit elements that are unimportant to this example because determining this current requires only that we know the power associated with the element and the voltage across the element. Now because the current arrow, the reference that we've set up for this current, enters the element on the side of the negative reference for the voltage, the equation for the power associated with this element is P equal negative IV. So if we want to determine the current would be negative power divided by voltage, and in this case the power is 40 watts and the voltage is 5 volts. So that gives us a current of negative 8 amps, which means that a positive current of 8 amps would flow from the direction of B to A, or a current of negative 8 amps flows from A to B. Now I'd like to talk about a very important property of power in electric circuits. Because energy must be conserved, and because energy is the integral of power over time, the total power absorbed by the elements in a circuit must be equal to the total power supplied by all of the elements. Because all of the elements that absorb power will have a positive power associated with them, and because all of the elements that supply power will have a negative power associated with them, another way to say this is that the sum of the power associated with all of the elements in a circuit must be equal to 0. Let's illustrate this with this simple example. So if we wanted to compute the total power in this circuit, we would do this as the sum of the power. There are 4 elements in the circuit. Let's call this element 1, element 2, element 3, and element 4. So this would be the power in element 1 plus the power in element 2 plus the power in element 3 plus the power in element 4. And if I wanted to be more specific in terms of the voltages and currents that are involved, this would be negative I1 V1, since the current reference is into the negative reference for the voltage. For the second element, the current reference is into the positive, so that would be plus I2 V2. For the third element, the current reference is into the positive reference, so that would be plus I3 V3. And for the fourth element, the current reference is into the positive. But it's worth saying something about this current I3. One of the things we haven't stated explicitly is that the current that flows into one side of an electric circuit element is always going to be equal to the current that flows out the other side. So the current flowing into element 3 is the same as the current flowing out of element 3. The current flowing into element 4 is the same as the current flowing out of element 4. And in this case, we've labeled that as I3. So this last power is plus, the current is entering into the positive side, I3 times V4. And that sum must be equal to 0. Well, let's see how we can use the conservation of energy principle to determine an unknown current in this simple circuit. So we begin by, again, writing down an expression for the total power. And the total power is the sum of the power in all of the elements. So for this element, we have 2 amps entering on the positive side of our reference for voltage. So that would be 2 times 6. So that would be 12 watts. For this element, we have I2, our unknown current, entering on the negative side. So this would be negative, let's write that as 6 I2. Now actually the units here should be watts, the units here should be volts. We'll bring those back in just a moment. This particular element has 3 amps on the positive of the reference over 2 volts. 3 amps through an element, 2 volts across it. That's going to be 6 watts. And this element has 3 amps coming through the positive side of our reference for 4 volts across. So that's going to be 12. And this total will have units of watts. So that tells us that this total sum would be 30 watts minus 6I2, and that has to be equal to 0. So that tells us that I2 is equal to 30 watts over 6 volts, which is equal to 5 amps. So by using the conservation of power, writing down our expression for the power, setting that equal to 0, we can find this one unknown current. Now if I2 was specified and any one other voltage or current wasn't specified, we'd be able to find that one too by using this constraint on the total power being equal to 0. Finally, let's be explicit about this relationship between energy and power. So the energy in any element of a circuit, or for the total circuit, that is the integral of power over a time interval. So if we want to know how much energy is supplied to the circuit from some particular time that we might call T1 and some particular time we'd call T2, we would look at the energy. The energy would be the integral of the power associated with that element over that time interval. Now the units for this would be watts times seconds. So we'd have watts times seconds, which would be equal to joules.